playtime. So the purpose of this is to explore the principles of Faraday's law and the electromagnetic induction by observing and modeling the motion of a bar magnet falling through a conductive aluminum tube. So to investigate the relationship between the magnetic field, induced current, and the forces acting on the system, we created a computational model. Our main results were that experimental time equaled 1.252 seconds, and the computational model equaled 1.632 seconds. Some fundamental physics principles were Faraday's law, Lenz's law, Biot-Savart law, and Newton's second law. And here you can see some of those. Possible error, magnet hitting the sides of the tube, time measurement and accuracy, and also air resistance. Below that, you can see a picture of the experiment. So some assumptions were that negligible air resistance drag is not affecting the fall time. Uniform conductivity, the aluminum tube is assumed to have uniform conductivity distributed throughout the volume. An ideal magnetic dipole, the bar magnet, is treated as a point dipole for simplicity in modeling. Our experiment with a bar magnet, aluminum tube, surroundings were everything else, and our initial conditions were that the north pole of bar magnet was facing downwards. So the magnet started at the top of the tube and the initial velocity was 0. Our procedure, for the setup, we held the aluminum tube vertically and positioned the bar magnet above its top opening. We used a smartphone to record the experiment, and then we dropped the magnet. So we released the magnet into the tube and captured its motion until it exited the bottom, and then we measured the time, so you can review the video to find the entry and exit times of the magnet, and we calculated the time that it took to pass through the tube. Then you repeat it to make sure that it stands up over time. So we performed the experiment 5 times and calculated the average fall time. And compare, observe how the magnet's motion differs from falling in free space. It's a little slower. These are our experiment values. Average time was 1.252 seconds. And as you can see, it went down and then went back up at the end, but it was mostly just going down. This is my computational model and the code that I used to do this. This is the actual model itself and the graphs that it created. So how do you know which is counterclockwise and which is clockwise? Red is CCW and blue is CW. And we use right hand rule. What happened with the dynamics of the system when you flip the magnet around? You get the same results. How does the total time into of your real world system compare to the computational? How can it be made more accurate? It's 0.38 seconds greater than our experimental value, and we have to take in miscellaneous factors such as air resistance or the magnet hitting the sides of the tube as it falls down if we really want to be more accurate. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar? It tells us that the bar magnet's first acceleration when falling through the tube, but then the magnetic force and the induced current counteracts the force of gravity. Bar magnet then falls at constant velocity for the duration of the tube. So what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? So it would greatly increase the braking or induced magnetic force, because by Ohm's law the induced current value would be much greater. This means the bar magnet would fall much slower. I equals V over R. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? So this would cause a disruption in the flow of current and less loops of magnet, which would weaken the braking force, and the bar magnet will fall much faster. Thank you for watching.